Okay, it is my pleasure to introduce our speaker, Maura McLaughlin. Maura is a professor at West Virginia University and an expert on neutron stars and their environments. And she's also a co-director of NANOGrav. And today she'll tell us all about the exciting new measurements recently made by pulsar timing collaborations.
Thank you, Gabby. Can everyone hear me okay? Great. Yeah, thank you so much for inviting me. It's really nice to be here, especially on such a beautiful day. So I'm going to talk to you about the recent results from the NANOGrav collaboration. The very big picture of our experiment is that we're timing an array of ultra-precise millisecond pulsars, and we're searching for very small correlated perturbations in the arrival times of these pulsars due to gravitational waves from the most massive black holes in the universe at the cores of galaxy mergers. So this little cartoon kind of shows like a big picture of what we're trying to do. And we had some pretty exciting results that we announced at the end of June this year. And if you want to sleep through the rest of the talk, this is the big picture. We've detected correlations between our pulsars that are consistent with what we expect due to a stochastic background of gravitational waves. And I'll tell you how we do the pulsar timing part of the experiment, how we search for these correlations, and then what this means, how we interpret this in light of the astrophysics of merging supermassive black holes and other sources. There was a lot of like really fun press coverage. I was amazed how much they picked up on it because it's kind of esoteric. I mean, when you look at this, this is like pretty esoteric. But there were a lot of headlines like this. Scientists say space-time churns like a choppy sea, and I think this one was my favorite. So just a little bit about the people who are responsible for this work. So I'm a member of NANOGrav. NANOGrav stands for the North American Nanohertz Observatory for Gravitational Waves. We were formed in 2008. We're about 200 students and scientists at about 60 institutions. We're a National Science Foundation funded Physics Frontier Center, and we've been funded as a PFC since 2015. We are also part of a broader international collaboration called the IPTA, or the International Pulsar Timing Array. And this consists of collaborations in North America, Europe, India, and Australia. We're just signing an MOU with South Africa, and we're talking to colleagues in China about hopefully getting them on board to also join this collaboration. And so the idea of this IPTA is that we combine data from all of the regional collaborations into one like uber, very sensitive international data set. And we have some funding from the National Science Foundation for this through this ExcelNet program. Okay, so why do we want to detect really massive black holes at the cores of galaxies? And the reason we want to do this is to understand how galaxies have evolved through cosmic time, right? So this is the standard picture of galaxy growth and evolution. Galaxies start off small, irregularly shaped. With time, we think they grow and become regularly shaped through mergers with other galaxies. So there's a lot of things that we don't understand about the processes happening at very close separations, right? So when we see a merging pair like this, we can study these electromagnetically, but we don't understand what drives these two black holes at subparsec scales to mergers. How much is gravitational wave emission driving them? How much do other astrophysical processes play a role? And of course, we can't study black holes at these separations electromagnetically. We need another tool, and that tool, of course, is gravitational waves. All of these galaxies, all the supermassive black hole binaries merging through the entire universe will be prodigious gravitational wave emitters. And so that is the goal of our experiment, is to understand this process by detecting gravitational waves from these very, very massive black holes. Just very briefly, an analogy with LIGO, because people are much more familiar with LIGO and how LIGO works. We know that LIGO has detected almost 100, maybe more now, compact object in spirals. A lot of those are black holes, but these are stellar mass black holes, right? So black holes with masses like a few, to maybe tens or 100 times the mass of the sun. LIGO is an interferometer with 4-kilometer long arms. And when a gravitational wave passes through this interferometer, one arm gets stretched and the other arm gets squeezed like this, right? Causing a change in light travel time along these perpendicular arms. The reason I'm mentioning this is just to illustrate that pulsar timing arrays operate the exact same way. Instead of using lasers, we're using pulsar pulses, but we're looking for changes in light travel time along the arms of a much bigger detector, right? So if we want to detect gravitational waves not from stellar mass black holes, but from billion solar mass black holes, we need a galaxy scale detector, and that is what a pulsar timing array is. So the goal of our experiment is to observe a network of these very precise cosmic clocks, radio pulsars, distributed across the sky. And we have about 70 pulsars we're observing now. So we have 70 arms of our detector. These arms are not 4 kilometers long, but thousands of light years long. And we're looking for perturbations in the arrival times of the pulses due to space-time getting stretched or squeezed in between the Earth and the pulsars. Okay. A kind of subtle thing, which I'm not going to talk about a lot, but I'll just point it out, is that these perturbations have a pulsar term. So what is happening when that pulse left the pulsar? What was the gravitational wave doing at that point? And an Earth term. What's the gravitational wave perturbation when the pulses hit the Earth? This is pretty cool. When we start to detect individual sources, we can actually sample a gravitational wave source at 2 different times in its evolution with these 2 different terms, which is pretty neat. And we search for very specific angular correlations in arrival times. This little cartoon gives you a basic idea of the kind of correlations we expect. So if pulsars are in the same direction, we expect correlated perturbations, right? So if a pulse from a pulsar in that direction arrives early, a pulse from a pulsar in that same direction should arrive early. At 90 degrees, because of the quadrupolar nature of gravitational waves, they'll be anti-correlated. At 180-degree separation, we expect a correlation again. This curve looks like this. This is called the Hellings and Downs curve. This was calculated all the way back in 1983. And so this is the exact shape that we're looking for in our pulsar timing data. It only goes to 0.5 because the pulsar terms for a background of gravitational waves, this is for a stochastic background of all the gravitational waves in the universe. All those pulsar terms are going to be uncorrelated, right? They're all at different distances. So it goes to 0.5 because we're only detecting the effect of gravitational waves on the Earth itself. And you can see there's some subtleties here when you do the math of averaging over all the sources and all the pulsars. This dip is at about 90 degrees, but not exactly. But you see this basic correlation at 0 degrees in separation of the pulsars, a negative correlation and anti-correlation at about 90, and a positive correlation at about 180 degrees separation again. So this is what we are looking for in our data. This assumes that general relativity is correct, and that this background of gravitational waves is isotropic. Okay. So we are sensitive to very low frequency gravitational waves. This is a plot of the gravitational wave spectrum. So this is gravitational wave frequency on this axis. And this is the characteristic strain of the gravitational waves. This is like, the delta L over L of the gravitational wave source. So stronger gravitational waves are up here. Weaker gravitational waves are down here. You can see LIGO here. This is the planned space-based interferometer LISA in this regime. And here our pulsar timing array is down here. So our strain sensitivity is about like 10 to the minus 15. You can understand that if you look at like the timing precision of our pulsars, it's sort of on average a couple hundred nanoseconds. You'll see this in a few slides. We've been doing our experiment for 15 years. That gets you around 10 to the minus 15. So that's where we come up with this strain sensitivity. These are sensitivity curves for NANOGrav in 2020 and NANOGrav in 2030. You can see that with time, we get more sensitive, of course, as we do our experiment for longer and longer. And our peak sensitivity here marches to lower and lower frequencies because it's 1 over the time span of our experiment. So we become sensitive to smaller and smaller frequencies as our experiment gets longer and longer. You might be asking, with this big spike here, this is a frequency of 1 over a year. We're not sensitive to any periods of a year in our data set because we would fit them out when we fit for astrometric terms in our pulsars. You'll see, oops, it's actually really hard to see on this slide. That's weird. Okay, so there are actually, you totally can't see them at all. There are populations drawn here of backgrounds, and you cannot see it all. But anyway, there's a picture of the stochastic background here, which looks like this and increases at lower frequencies. So we expect more stochastic background at low gravitational wave frequencies. This equation gives you the strain of a binary as a function of the mass, the frequency, and the distance. we expect the stochastic background to have a red spectrum, so more power at low frequencies. So even though the lower frequency binaries have smaller strains, we expect there to be a whole lot more of them. And I swear they're actually like rectangles underneath all three of these curves, and they don't show up on the screen at all. I'll remember for next time. We'll come back to this though. Okay, so that's the like super big picture overview. What we're trying to do, the correlations we're searching for, what our goal is. Now I'm going to talk a little bit in more detail about our actual experiment. So I'm a pulsar timer, so my individual effort in NANOGrav is mostly focused on this part of the experiment, on timing pulsars, modeling pulsars, characterizing the noise in pulsars. We observe about 70 millisecond pulsars right now. So millisecond pulsars have periods from about 1.5 to 10 milliseconds. That's the range of the spin periods of the pulsars we observe. We have to observe them over a fairly wide range of radio frequency. This helps us correct for interstellar medium delays, which are frequency dependent. So right now we're observing from about 400 megahertz to 3 gigahertz. Currently, our observing program is very focused on the Green Bank Telescope in West Virginia. This is the one in my backyard. And we've recently started adding data from the CHIME telescope in Canada. You've probably heard of CHIME with relation to fast radio bursts. It's done a lot of amazing FRB science. It's also a great pulsar instrument. We have a small program with the Very Large Array in New Mexico, and we have a very small program with the FAST telescope in China. For many years, our two real workhorse telescopes were the GBT and, of course, Arecibo. Arecibo and the GBT both did about half of our pulsars, and the results I'm going to talk about today end when Arecibo collapsed. So our 15-year data set that I'm going to talk about today, we cut that data set off on the day that we lost access to Arecibo. So our current program includes CHIME, FAST, the VLA, but the data I'm going to be talking about are mostly Green Bank and Arecibo. Arecibo's collapse was obviously a huge loss. Roughly half our sensitivity came from Arecibo and half from the GBT. Just a reminder, Arecibo did a ton of amazing things, and I have to mention Arecibo because, of course, Joe Taylor got his Nobel Prize with the binary pulsar discovery with the Arecibo telescope. So it's made a ton of amazing contributions over the years. And when we lost it in August 2020, we lost the observing capability in August 2020 when a cable broke. And then in December 2020, I'm sure you've all seen the video of the collapse. That was when we lost access to it entirely. And it's really a huge tragedy for science and for the people of Puerto Rico. We're also part of a worldwide pulsar timing array observing program. This is the IPTA program that I talked about earlier. These telescopes all over the world are carrying out this experiment. Telescopes in Australia, China, India, South Africa, and North America all have independent pulsar timing array programs ongoing. So let's talk a little bit about pulsar timing. Like, what do I mean by pulsar timing? This is a very simple cartoon that explains the concept. So at every epoch, we observe a pulsar. With the GBT, that's about once a month. We add up all the pulses from that pulsar over something like a half an hour observation. And we call this folding the data. So these individual pulses will be hidden in a lot of noise. They're generally too faint to detect individually. We sum them up at the pulsar period. We calculate a very high signal to noise folded profile at each epoch of observation, and we calculate what we call a TOA, or a pulse time of arrival. And then we have a model, right, that incorporates all the astrophysical stuff affecting those pulsars' times of arrival. And at another epoch, say session J, which might be a month later, we do the same thing. We fold the data, we calculate a time of arrival, and then we calculate a timing residual, which is the difference between when the pulse arrived at this session and when our best model predicted it should arrive, right? And so these residuals are what we analyze to search for gravitational waves, because we're looking for non-zero residuals that might be due to gravitational waves that are correlated among our pulsars. So that's the basic idea of pulsar timing. All of our data is public. Any of you can go to data.nanograv.org. You can download all of our times of arrival. You can download parameter files that have these astrophysical models. You can download pulse profiles like this. If you download the times of arrival, you will get a text file that looks like this with radio frequencies, modified Julian dates out to some huge number of precision. These are the errors for this particular pulsar in microseconds on these arrival times. And you'll also get a file that looks like this with the timing model for that pulsar. For this particular pulsar, you can see the spin frequency that we measure is referenced to a particular epoch here. And it's 218.8118404171579 hertz. And we really do know that down to that like very last significant digit. Yes. Yes, so that's a really great question. So we correct all our arrival times to the solar system barycenter. So one really important part of our experiment is having an ephemeris for the motion of the Earth and all the other planets in the solar system. And so we use these ephemerides from JPL to correct all the arrival times to the solar system barycenter. And that's a great question because we actually had a problem with one of our data sets when we realized the ephemerides weren't accurate enough, and we saw a correlation among the pulsars that wasn't gravitational waves, but it was due to this ephemeris actually not being accurate enough for our purposes. That's a great question. Yeah.
There's time variable dispersion measure along the line of sight at a small level. You know this because you have the multi-frequency data? Is that...
Yeah, so I work on this particular aspect a lot. Modeling dispersion measures, that's something that I do a lot. I don't talk about it much in this talk, but it's one of the major sources of noise, is correcting for these delays through the interstellar medium. They have an exact frequency to the -2 dependence. So with enough of a lever arm in frequency, if we observe at enough frequencies, we can distinguish those kind of delays from, say, gravitational wave delays, which aren't dependent on radio frequency. But there's a whole industry. We still are not, 100% converged on the absolute best way to fit for those time variable dispersion measures. We can do it at each epoch. We can fit a Gaussian process. There's a lot of research ongoing.
Static, or is it subdominant at the moment?
Subdominant. Yeah. I mean, it will increase our precision if we can make sure we're doing it right. But it's not a dominant source of error right now. Our dominant source of error, just to be clear, is just the sensitivity of our radio telescopes, honestly, at the moment. We just need, if we had bigger, better telescopes, that's the #1 way we could do better right now. So this is a little illustration of our data releases. So our first data release was after 5 years of data, and we had 17 pulsars. This is a little snapshot here. So these are pulsars along this axis and time. The different colors are just different telescope frequency combinations. We had a 9-year release with 37 pulsars, our 11-year had 45, our 12-year had 48, and then our most recent 15-year release had 68 pulsars. And so we've grown the number of pulsars with time through pulsar searches with radio telescopes. And so you can see we've just continually added to this array, which makes us much more sensitive. These are the kind of data that we analyze to search for gravitational waves. So these are pulsar timing residuals for 3 different pulsars. Again, the different colors just show different backends at the different telescopes. These 2 pulsars we observe with both Green Bank and Arecibo. So you see things that start with A for Arecibo, or P for Puerto Rican, and G for Green Bank. So these are just different backends on the telescope that have different radio bandwidths. With time, our error bars have generally gotten smaller because we've moved to larger and larger radio bandwidths. You'll also see our cadence has increased. These points are much more finely separated than they were at the beginning. We've got a lot more observing time on the telescopes to observe more frequently. So what can you see here? The first thing to notice is that the scale of this axis, this is in microseconds. So the root mean square of these residuals is well less than a microsecond. The other thing to see is that they're mostly hugging 0, which means that our models are doing pretty well. The other thing you'll notice, though, is not always. There are some residuals that lie off of 0. You might also imagine you can see some kind of variable structures in here. But this is the best we can do with our deterministic timing model. And if there are gravitational waves in here, they will be very low level effects that we will only see when we cross-correlate the residuals from different pulsars. So what will those look like? Well, we expect the stochastic background. And again, this is the sum of all the gravitational waves from all the supermassive black hole binaries in the universe. We expect that to have most of its power at very, very low frequencies. So if we looked at timing residuals versus time, we would expect this to be a very long time scale perturbation on our pulsar timing data. So this is what it would look like before we fit for any of our pulsar timing parameters. After we fit for those parameters, though, we're going to absorb a bunch of this into our timing model. We can't help it. And so after fitting, it'll look something like this in our data, sort of like a red noise kind of quasi-periodic structure. Yes?
So
Yes. Oh, good question. Yeah, I should have explained that. Yeah, so the different lines are different pulsars in different directions of the sky, the different colors. We can also search for individual gravitational wave sources. So gravitational waves from a single supermassive black hole binary in that direction with a particular period. This would look the same before and after fitting, because it's not going to be covariant with anything in our timing model unless it has like a period of exactly a year, which would be unlikely. So these will be preserved after fitting the timing model exactly in the same form. And you can see that these different lines for different pulsars, in this case, they'll have the same period, but they'll be offset in phase and amplitude depending on the angle between the Earth and the pulsar and the gravitational wave source, right? So we have some directionality in the pulsar timing experiment, just like we want multiple ground-based interferometers, multiple pulsars give us the localization capability, which is pretty cool. Okay. So in addition to the deterministic stuff in that timing model, so in the timing model, I don't know, they're just so cool how well we can measure all these things. Like we have deterministic things like, right ascension, declination. Look at all those significant digits. Proper motion, binary parameters. Most of our pulsars have white dwarf companions. So you can see all these binary parameters here. This is the orbital period in days, 67 days. There are some things that are noise, right? They're not deterministic like the things in that model. Some of those things are the planetary ephemeres, variations due to the interstellar medium, pulse-to-pulse jitter, the fact that our pulses are not exactly stable, they're kind of like jumping around in phase, pulsar rotational irregularities, the pulsars aren't like perfect spinners, right? They have some superfluid core, which transfers angular momentum to the outer layers occasionally. We could have errors in the clocks at our observatories, but the important thing is that we can distinguish the gravitational wave background from all of these things by searching for different effects in the data, right? So these interstellar medium effects depend on radio frequency. They're not achromatic. Pulse jitter is not correlated in time from one epoch to another epoch, but the other ones are. The planetary ephemeris errors are the only other ones that would show a correlation in space, but they wouldn't be quadrupolar like gravitational waves. They would be dipolar, right? If we have an error in the mass of Jupiter, for instance, we would expect an anti-correlation at 180 degrees, not 90 degrees. So this is how we do our noise modeling. It's way more complicated than just this table, but we can distinguish different sources of noise by modeling their properties. This is what comes out of that kind of noise analysis. So this is a noise analysis for one of our pulsars. And what you can see here, these orange regions here, these are the posteriors on the spectrum for this particular pulsar, the spectrum of its residuals versus frequency. And then we model it with different contributions. So there's a white noise contribution. This is a really good timer, so this particular contribution is pretty small for this pulsar. This pulsar also has pretty low levels of individual red noise. So this is the individual red noise contribution. And then what we really want to constrain is this common red noise. So this CURN stands for common uncorrelated red noise. So this is the common red noise that this pulsar has in common with all the other pulsars in the array. We see this common source with the same amplitude and spectrum in every single pulsar. And so this is that common red noise. And then what we do is we ask, how are we doing at this modeling? Like, are we modeling all the noise with all these sources? This shows base factors at all these different frequencies for the excess noise. Like, is there any excess noise that we're not getting at through our model? And we can see these base factors are all at about 1 or below, which means like we're doing a good job for this particular pulsar of modeling the noise through these different contributions. So this gives us high confidence in our understanding of the noise and our modeling of the noise in these pulsars. So I'm going to talk about the gravitational wave analysis now. So our most recent data set, the one that we announced back in June, is the 15-year data set. But I'm going to talk just a little bit about the penultimate data set, the one just before this, because it's just kind of like a nice story. It motivates why we did the 15-year analysis the way we did. So what we do when we do these analysis is we calculate a probability density for a particular gravitational wave amplitude in our data. So this CP stands for common process. So this is the amplitude of this common noise process in the data. In our last data set, the 12.5-year data set, we were very excited because we detected a common process among all the pulsars in the data set. So when we did this kind of noise analysis, we saw this kind of signature in all the data, a red noise process with a particular amplitude and spectrum that was detectable in all of the pulsars. That was really exciting. It peaked at a very particular gravitational wave amplitude. These different curves are different solar system ephemeres. These are two different fixed ephemeres, and this is a Bayesian method we use for modeling the ephemeris. This doesn't matter too much. The important thing is just that we detected this strong common process in the data. However, when we search for the correlations that we expected due to gravitational waves, we got this. So these black points here are the binned pairwise correlations for all the residuals from all the different pulsars, and this blue dotted line, this is what we would expect due to a gravitational wave background, and you can see that these points don't really hug that curve. We, of course, have a much more sophisticated statistical analysis that says they don't hug that curve. It's not just by eye, but you can see right here, there's no correlation detected there. So the upshot of that 12.5-year data set was there was a huge Bayes factor of over 10,000. So the common process was favored like 10,000 to 1 over individual red noise in the individual pulsars. So that was very exciting, right? It's what we expect for gravitational waves, but we couldn't say for sure it was gravitational waves because we didn't see this signature in the data. The really exciting thing about this was that our international collaborators saw this same thing. They all saw this common process. These are spectral constraints from the International Pulsar Timing Array collaboration. This is the spectral index of that red noise and the amplitude of that red noise. This was the Australian group, the PPTA. This is the EPTA group. Everyone sees similar spectral constraints with a very large Bayes factor for this common process over independent pulsar noise. And a large Bayes factor for the common process over a monopolar signal, so like something that doesn't depend on angle, or a dipolar signal, like we might expect for an ephemeris. So this was really exciting. It looked like gravitational waves, but we didn't see those correlations yet. So after we all saw this signature in our data, this common process, we started the undertaking of an absolutely huge, coordinated international effort. So groups all around the world decided about 3 years ago now, we're going to all process our most recent up-to-date data sets. We're all going to search for gravitational waves in those data, and we're all going to wait for each other and publish those results together because they'll be much more powerful if we work together and coordinate those publications. I'm frankly still amazed that this worked. I mean, it was like a very long process, but it worked. So on June 29th, there were 18 papers that simultaneously all appeared on the archive. Many of them also accepted, some of them not, some of them still waiting for acceptance, but all on the archive at the same time on June 29th. You can see some of those are NANOGrav papers. Here's our gravitational wave background paper, a bunch of other papers that accompany the background paper, European Pulsar Timing Array, Parkes Pulsar Timing Array, this is the Australian group, and the Chinese Pulsar Timing Array paper. So a whole bunch of papers all out on the same day, which was really, really exciting. I'm going to focus mostly on NANOGrav results, but I'll talk a little bit about the international context as well, which is really important. So I showed this plot. I think this was the second slide that I showed you. Here it is again. So this was the upshot of our 15-year stochastic background analysis. So this is not the kind of like plot that we use to do the analysis. When we do this analysis, we use all 67 pulsars. That's 2,211 distinct pairs. Oh, that should be pairs. Don't know, was it like a Freudian slip? I'm not sure. It should be pairs, not panes. But in this particular plot, we've just binned them just like for ease of viewing really, but we don't analyze this, binned version at all. This may not look like much when you look at it, right? The error bars are kind of big. But we were incredibly excited when we saw this. We've been looking for a signature like this for 15 years. So the important thing is we see a positive correlation at low separations, a negative correlation at around 90 degrees, and a positive one at 180 again. So this is really, really exciting. If we actually do a little bit of statistics, we can do statistics in either a Bayesian or frequentist way. We've tried a whole bunch of things to estimate the significance of this signal. This plot here shows the result of phase shifts. So we basically take those residuals in Fourier space and just shift them in phase with respect to each other, and then do the analysis again and again to see how many times we recover a signal as that matches the curve as good as that previous plot, right? So we just like shift the data up randomly, see how long it takes to get that similar signal. So this shows the Bayes factor of the Hellings and Downs over an uncorrelated red process. Here's our Bayes factor. This shows the results of the simulations. So this shows it's like 3 sigma-ish. Here's a frequentist approach. Do the same thing. We just estimate things a little bit differently. We use the signal to noise of the Hellings and Downs instead of the Bayes factor. And you can see it's sort of closer to a 4 sigma result when we shift things that way. And we've also done a whole bunch of other stuff like moving the pulsars around in the sky. We call that sky scrambles, like a whole bunch of different things to estimate the significance. And in general, we come out with numbers that are about 3.5 to 4 sigma for the significance of those spatial correlations in the data. One important point is the Bayes factor is over 10 to the 12 for the common process over independent pulsar noise. So we have overwhelming evidence that there's a common noise process in the data. And the spatial correlations are detected at lower evidence, which is expected for the early stages of a gravitational wave background signal emerging. This is the kind of like thought process we do when we estimate the significance. So, you know, we had this 10 to the 12 Bayes factor for the common process over intrinsic noise. Doesn't look dipolar. It doesn't look monopolar. We have a Bayes factor of somewhere between a couple hundred and 1,000 for the Hellings and Downs curve over just the common process. And then we test different types of spatial correlations, like what happens if we add a dipole to that Hellings and Downs curve, or a monopole, or a sine wave, which is what we might expect for like a single source. And we see in all these cases, this Hellings and Downs common spectral process is preferred over any other type of spatial correlation, which is pretty exciting. So what can we say about the astrophysics? Well, this is a plot of the spectrum. So these gray regions here show the spectral constraints at a number of gravitational wave frequency bins. Looks kind of like a power law. So this is the posterior we get when we fit a power law to the data. This dotted line here shows the expectations for a gravitational wave background from inspiraling supermassive black hole binaries under the very simplest assumption that their in-spiral is completely dominated by gravitational wave emission, right? So they're only getting closer and closer and closer due to the energy loss from gravitational waves. And in that case, we expect a spectral index of 13/3, and you can see that dotted line here. Ours is pretty consistent, but a little bit shallower. What we think that means is that there's other astrophysics. There are some environmental interactions that are also at play in bringing these black holes together. It's not just all gravitational waves, but it looks, you know, more or less consistent. Intriguingly, this red spectrum is also consistent with lots of other exotic things. It could be from primordial gravitational waves, from early universe inflation, cosmological cosmic strings could cause something like this, domain walls. I'm not going to talk any more about this because I will very quickly get out of my expertise, but there's like hundreds of papers that have been published since our result on different sources. And it's interesting, there are way more of these papers than papers on the supermassive black hole binary origin. So this exotic physics is of a lot of interest to people. And right now, it's kind of fun because our errors are big enough that you can basically explain it with almost anything. They just pick a favorite model. So what we see is consistent with the signals seen in the other pulsar timing array data, which is very reassuring. So this shows the different colors of the different PTAs. The orange is NANOGrav. The ePTA and the Indian PTA combine their data for their analysis, and this is the Australian group. So this is spectral index versus amplitude. They're not like perfectly consistent. You can see that the blue contours are shifted a little bit with respect to nanogravs, which is shifted a little bit with respect to the PPTA. That's expected. It's probably due to slightly different ways of modeling the noise in our data. But they're all broadly consistent. We all see this red spectrum. This shows the overlap in pulsars between the different data sets. We have a lot more pulsars. The data sets are not completely independent, right? So some of the pulsars are the same between all three of these data sets. Some of them are independent, and the telescopes themselves are all independent, right? So we're immune to sort of like telescope-specific issues. So what can we say about supermassive black hole binaries? So this was kind of like the main motivation for doing this experiment. And we can say quite a bit already, actually, just from our initial measurements, and we'll be able to say a lot more with time. I do not have time to go into this in any detail whatsoever, but it just gives you an idea of like our process for understanding supermassive black hole binary populations. So we simulate populations with a bunch of different assumptions, right? So we have some stellar mass function. We have a galaxy pair fraction. That's the fraction of galaxies that have a black hole binary pair. We need a merger timescale. This MT is the merger timescale. We need to assume a relationship between the black hole and the bulge mass for galaxies. These are just examples of the kind of astrophysical constraints. There's a bunch of different black hole bulge mass relationships that have been published. And then we evolve those binaries under the gravitational wave only scenario, or a scenario with lots of other astrophysics going on, like a disk or stellar scattering, for instance. We have code that does this, blah, blah, blah. And anyway, we go through, these are different ways of modeling the DMs, this DM Gaussian process. So there's a whole bunch of different branches of this. And in the end, what we do is we produce simulated supermassive black hole binary models, and we compare them to our detected background, right? So what is the background produced by these different simulated models? How does it compare to our background? And then we can say things about supermassive black hole binaries. So this plot shows a couple properties of supermassive black hole binaries. The total mass of the binaries, the mass ratio, their initial redshift, the final redshift when the merger happens. And the dotted lines are the number of binaries contributing, and the solid lines is the contribution to our stochastic background. This is too complex to go into in a lot of detail in this talk, but the basic gist of it is that large mass binaries are contributing to the stochastic background. So binaries with masses of like 1 billion to 10 to the 10 solar masses, binaries with roughly equal mass ratios at redshifts of about 1 or so are the supermassive black hole binaries that are contributing to our signal. This plot over here, which is also very light, shows some of these same parameters. This band over here are the priors on those parameters, and the blue curves here are our posteriors. The only thing to take away from this is that our posteriors are at the upper end of masses. And the upper end of distances. This shows a bunch of papers that have been published, like predicting what the background should be for different astrophysical models. This is our amplitude. And you can see most of those papers lie below our amplitude. All of this means that the amplitude that we detect is on the high side compared to model predictions. It's not unreasonable. It's still consistent. We can still make it happen with supermassive black hole binaries, but generally higher masses are favored. Closer distances are favored, and just like more binaries are favored. I see your question. I'll get to it in 1 second. One important point, though, is right now we don't know if our background is purely due to supermassive black hole binaries. There could also be other contributions, and we can't discriminate that right now. But right now, we need sort of like high masses, lots of binaries, close binaries. Yes?
So presumably, given the range of frequencies that you're sensitive to, there's a mass range over which you are sensitive as well. So when you say high masses are favored, to what extent can you probe other ranges of mass? That's
a good question. So like, for instance, we're not really sensitive to million solar mass binaries. They would be in LISA's range of detectability. So when I say high masses are favored, what I'm really meaning is we have like a galactic stellar mass function. So like a DN-DM of the number of binaries at different masses. And it just needs to have a slightly steeper slope than most models, right? So just like more masses at the lower end of that stellar mass function, basically. Yeah. So the pair fraction? Oh gosh, what are our current estimates? Do I have it on here? I don't have the pair fraction on here. I'm embarrassed I don't remember the exact number. I mean, it's pretty high. It's like, yeah, I heard an answer, but I should know this, but like it's more than 10%. I mean, it's high. I don't remember the exact number though. Yeah, I will look it up for you. Yeah, I should know that offhand. I don't remember the number. So yeah, and one point I'll make about this is many of these are like astrophysically motivated. You know, many of the numbers that we pick as the priors for these, you know, they all have some astrophysical motivation. Some were measured nearly exactly, and some were really just guessing. So I should wrap up pretty soon. So, you know, I mentioned like we don't know for sure that this background is due to supermassive black hole binaries. We think it's very likely it is, or at least mostly due to supermassive black hole binaries. We know that they exist. We know they emit gravitational waves. There's lots of observational evidence. But it's also quite possible that there are multiple contributions. So we might have a supermassive black hole binary stochastic background combined with one due to cosmic strings or from primordial gravitational waves. How are we going to distinguish them? Well, there's a couple different ways. We can't do it now, but in a few years, we should be able to look for different spectral slopes in the data. So this is a project that a grad student working with me named Andrew Kaiser published last year, where he simulated a second gravitational wave background with an amplitude like half the primary one. And in about, you know, the 20-year data set, so in about 5 years, we should be able to detect that second background fairly significantly with a Bayes factor of like 100 to 1,000 and a reasonable fractional uncertainty on the spectral index that we can actually say something useful. So in about 5 years, we should be able to discriminate like multiple backgrounds. Another really important clue to the origin of the background is that we know that supermassive black hole binaries will not be exactly isotropic, right? They're going to be, you know, these are discrete sources. It will not be a perfectly isotropic background. So we actually don't expect perfect adherence to that Hellings and Downs curve for the case of a supermassive black hole binary background, right? It won't look exactly like that because it'll be a little bit anisotropic. These other sources, cosmic strings, primordial gravitational waves, they should be totally isotropic, completely isotropic. So this is another analysis that was done by postdoc Nihan Pol, and this shows that, again, at about the 20-year baseline, we should be able to discriminate between the isotropic background, this is the isotropic signal to noise, and the anisotropic signal to noise, which will have a signal to noise of like 3. So this is like the bit of the signal that's anisotropic. We should detect with a signal to noise of 3-ish in the 20-year data set, assuming it's like 30% anisotropic. This is a very particular assumption, but this just kind of roughly shows, you know, in about 5 years, we should be able to tell whether it's perfectly isotropic. And just finally, I don't have much time to talk about the continuous wave results. So the stochastic background results are the most interesting because we see something, but we're also searching for single sources of supermassive black holes, single supermassive black hole binaries in the data. And so the way we do that is we look in different sky directions, and we can search over a range of periods and amplitudes and all those different sky directions, and we make maps like this. So this map is in units of luminosity distance in megaparsecs, and you can see that we can place constraints on black holes of 1 billion solar masses out to almost like a couple hundred megaparsecs right now. So like in this particular direction, we can say there are no supermassive black hole binaries with masses greater than 1 billion solar masses in our frequency range, you know, out to about 160 megaparsecs. The red stars are the pulsars. The other symbols here, these are putative supermassive black hole binaries. So galaxies, which electromagnetically have features that suggest they have a supermassive black hole binary at their core. And so we will continue to do this experiment looking for these individual sources. One pretty cool thing that we can do is if we've identified a possible supermassive black hole binary electromagnetically, we can take the electromagnetic parameters as priors and feed those into our analysis. So if we already know a distance or an orbital period or an estimated mass, we're much more sensitive because we can search over a very narrow range. One of these is called 3C66b, and I really should have put the name of this galaxy on this plot somewhere. But this shows the kind of work we can do. We can set upper limits on mass on an electromagnetically identified source. So this dotted line here is the electromagnetic guess on the mass based on radio observations of this galaxy. It's about 800 million solar masses. These are our upper limits from our 12.5-year data set calculated in slightly different ways. We haven't done the 15-year analysis yet for this galaxy. When we do, it should be right around here. So we should be like very close to detecting the supermassive black hole binary in this galaxy, or saying this electromagnetic limit is wrong. So let me just end by talking about the goals for the future. So how are we going to become more sensitive? What do we want to do over the next, say, decade to really push this field farther now that we have this like initial evidence for these gravitational waves in our data? What's next? Well, gravitational wave sensitivity is linearly proportional to the number of pulsars. So we want to grow the number of pulsars in the array. And our goal is to get to something like 200 millisecond pulsars by 2030. This just shows the signal to noise and those Hellings and Downs correlations versus the number of pulsars. And you can see these linear trends. Don't worry too much about these sigmas. These are the cross-correlation uncertainty. But we think we're up in this regime where we will see very significant increases in sensitivity with more pulsars. We also have some really exciting observational advances on the forefront. So at the Green Bank Telescope in West Virginia, the Moore Foundation has funded a new receiver, which is a wideband receiver. So right now we observe from 800 megahertz, from 700 megahertz to 900 megahertz in this little regime here, and from 1100 to 1900 megahertz in this regime here. We have two receivers that cover this. This wideband receiver is going to cover this whole span, right? So this is data from a pulsar showing emission all the way from 700 megahertz up to 4 gigahertz, and we're going to get all of this soon. This is going to be a huge sensitivity increase for us. It'll make our observing way more efficient too, because we don't need to observe twice, like once with this receiver. Once with this receiver, we can just do the whole thing. So this is very, very exciting. We're working really hard also right now to incorporate the data from the CHIME telescope into our data set. Our last data set didn't have data from this CHIME telescope. This telescope observes every single day. With the GBT, we only observe once a month. With the CHIME telescope, we get it every day. This shows residuals. These are dispersion measurements. The green and blue points are the GBT data, and the yellow points are the CHIME data. You can see there's way more of them. You can see that the error bars on these dispersion measurements are way smaller than we get with the GBT. This is because CHIME is at a lower frequency, and so it can measure those interstellar medium effects better. So we're really excited to see the impact of including this data in our data set. It should make it much more sensitive. We really need a new telescope. Our sensitivity took a huge hit with the loss of Arecibo. We can't get enough time on the GBT to cover all of our pulsars. It's not sensitive enough to cover all of our pulsars. One telescope we're pretty excited about is the DSA 2000 telescope. This would be an array of 2,000 small dishes in a valley in Nevada. It'd be about Arecibo collecting area. We hope to get about a quarter of the time for this. And I don't have much time to talk about this, but this just shows that, you know, if we simulate single source populations, so this gray regime here, these are single source strains, so single supermassive black hole binaries. Here's what we get if we just extend our current obs. This is what we get if we build this telescope. And so these are in 2036. If we build this telescope, we're going to get much more sensitivity to a whole population of these single sources that we would not have otherwise. And another huge focus is, of course, growing this international collaboration. So the way the IPTA works is we take all the individual data sets from all the different, you know, regional collaborations, and we put them into like one Uber data set. We're working on DR3 right now. So this is the IPTA third data release. It's going to contain all of the data sets that I showed you that all have this common process and this spatially correlated signature at some level of significance, plus new data from the Meerkat telescope in South Africa, and this CHIME data from the CHIME telescope in Canada. So this should be much more sensitive than our current data set. It should result in a very strong detection of these correlations. And the IPTA DR3 data set should also be very sensitive to single sources. It'll have over 100 pulsars, and this shows the sensitivity of the IPTA data sets in 2025, 2030, 2035. These dots here are simulated supermassive black hole binary populations. Even in 2025, there's a chance that there will be single sources that lie above our sensitivity. This is this 3C66b. We should definitely see it in this DR3 data set if the electromagnetic predictions are correct. And there should be a whole population of these single sources that we're sensitive to in these future data sets. And that'll be really exciting to be able to observe galaxies electromagnetically and in gravitational waves and compare the properties. We'll learn an awful lot about galaxy evolution. and the astrophysics of supermassive black hole binaries. And I will just end with this pretty picture, just illustrating that the goal is true multi-messenger astrophysics, observing pulsars with radio telescopes, observing host galaxies all the way from radio to gamma ray energies, and then at the same time measuring gravitational waves from the binaries at the cores of those galaxies to form a very complete picture of supermassive black hole binaries, and of course, other exotic sources of gravitational waves. And so I will end there. Thank you very much. Should I navigate the questions? Thank you.
So I'm not sure if I'm supposed to be speaking, but the extreme scattering events, as you know, have been interpreted in terms of blobs of plasma moving across the line of sight to extragalactic sources. In that model, and assuming that these blobs of plasma are closer than the pulsars and not beyond them, would you have expected to see events like that in your data set?
Definitely. Yeah, definitely. And I'm talking about something similar to that at the lunch after this, because we have seen, a few really weird kind of cusp-like events in our DM time series, which may be due to something like extreme scattering events. The good news is they have a very strong radio frequency dependence, so they don't look like gravitational waves. The bad news is they do mess up our timing data. They are sometimes difficult to model. But we have seen a couple interesting things like that. In this data set, like you can write multiple PhD theses, not even on the gravitational waves, right? But just on like this scattering and DM variations.
Very nice talk. I had a question about the slope when you were comparing the slope from gravitational waves, which is -13/3, I presume, and what you actually observed, which is a little shallower than that. And you mentioned that that can be due to astrophysical effects like environmental effects. Can you comment on why that would produce a little shallower slope and not a little steeper?
So basically, if there's other stuff, like say there's gas or stellar scattering that makes the binaries merge faster, right? So if there's other astrophysical effects that can make the binaries merge faster, say they're in like a disk of material, and they're going to just move through that frequency band faster and just decrease the total amplitude. So it's not decreasing like the number of binaries or the mass, but the merger time scale is going to be shorter, and they're just going to spend less time in the band, and that slope's going to be like, a little bit lower. The signal will be a little suppressed in that part of the band. Does that make sense?
Always make it happen faster. Why can't, like, I presume you were talking about dynamical friction and things like that. So why can't dynamical friction be a little weaker than what you have in your model?
Well, the 13/3 assumes like no astrophysics whatsoever. Like it's just gravitational waves. And so like there's absolutely nothing but just purely gravitational wave merging. So what was seen for like the Holz-Taylor binary, basically just like the most simple thing in a very clean system.
There was a significant improvement from 12.5 to 15 years. That's not a big jump in time. So how does your sensitivity and whatever metric you want to invoke go with time?
Yeah, so we're not sure exactly. So it goes roughly, we think, linearly with time, roughly. But it's a little bit complicated. It depends on the ratio of like the strength of the background to our sensitivity. So there's it's hard to have an exact relation, but we think roughly linearly with time. The important thing but you're right, from 12.5 years to 15 years, that's not a lot of time. But we went from 47 pulsars to 67 pulsars in the gravitational wave analysis. And our sensitivity improves linearly with number of pulsars. So that was really the most important thing. There's also a little bit of improvement in like noise modeling and algorithms, but the main thing is that number of pulsars actually.
This common red noise that doesn't seem to be angularly correlated in the way gravitational waves would be. What are the top few leading candidates for the sources of that? And could it be something geophysical?
Yeah, so we don't think that there is common red noise that is not gravitational waves. So we think all the common red noise that we see is gravitational waves.
The quadruple signatures, I mean, you have a very highly significant detection.
Yeah.
But a weakly significant, well, 3.5 significant.
Yeah. So again, we think all the common red noise is due to gravitational waves, but we can't be sure. But it's just much more difficult to detect the spatial correlations in the data than to detect the common noise in a spectral analysis. Part of that is that all of these pulsar terms are a source of noise for the spatial correlations. So, you know, when I showed the picture of like what's happening at the pulsar and what's happening at the Earth, that's a huge source of noise for that Hellings-Downs curve. The other reason is it's just, well, there's a couple of reasons. It's much more difficult to detect the spatial correlations in the data versus just this common noise, just because of the pairwise way we do this analysis. We don't have like perfect sampling over that kind of like pulsar angular separation axis. We have many pulsars that are brighter in one part of that curve than the other part of the curve. It's just statistically much more difficult. But we don't think it's source. I think it's all gravitational waves.
So I have two very short questions.
Yeah.
The first one is there's some discussion in the blazar community that blazars might be driven, at least the variability might be driven by binaries. I guess you've looked at the closest blazars like Markarian 501 and 421, and these are 130, 140 megaparsecs, and these are still, I guess, too distant for any kind of detection, are they?
Yeah, I mean, so far they're either too distant or the separation is just too like wide. We need like supermassive, you know, the pairs need to be very, very, very close, and they need to be really, really massive, like billions of solar mass. A colleague of mine at WVU, Sarah Burke-Splar, she and a student of hers named Jessica Sidner, they're making a database called Bobcat. So it's a black hole binary catalog, which is going to have all these things in there. And so we hope the community can add kind of their favorite possible supermassive black hole binary sources to this catalog. And we'll get into like a factory mode soon, where we're just kind of going through and setting electromagnetic constraints that are constantly updated as we get more and more data. And we're setting gravitational wave constraints on our electromagnetically identified sources. So you should check out this catalog. I can tell you more about it if you want to talk about it after.
What was the motivation for building a new telescope array in the SKA era?
So are you asking like we're going to have the SKA, so why build something else? Because we don't want forever. I mean, this DSA 2000 telescope is on a very short time scale. It's extremely aggressive. So there's been a pre-proposal to the NSF MSRI program that was successful. A full proposal is going in January, asking for 88 million, and it'll be built by 2027 if this proposal is funded. So it's very cheap because it doesn't do all that SKA will do. It's like very specialized, but it's very cheap to build. It can be built very quickly. The way our pulsar timing experiment works is we really depend on like maintaining our timing baselines on these pulsars, and we've already lost some with Arecibo, and we need to get the time now. Like we can't wait for the SKA. So that's really the motivation. Yeah.